Why are strain nanomaterials better than regular nanomaterials? Imagine a rubber band. When you stretch it, it becomes tighter and more powerful. Strain nanomaterials work in a similar way. By applying strain, stretching or compressing these tiny materials, we can enhance their performance significantly. For example, in nanoelectronics, strained graphene acts like a supercharged racetrack for electrons, allowing them to move faster and making computers quicker and more powerful. In nanophysics, strained silicon nanowires function like upgraded electrical wires that carry more current without overheating, improving electronic device efficiency. In nanophotonics, strained quantum dots are like tiny light bulbs that change color when pressed, resulting in brighter and more colorful LED displays. In quantum computing, strained materials fit together more perfectly, enhancing their ability to perform complex calculations. In nanochemistry, strained materials act as super-efficient catalysts, speeding up chemical reactions for faster and cleaner industrial processes. By applying strain, these nanomaterials become extraordinary, unlocking new possibilities across various technological and scientific fields. At the heart of this revolution lies a simple yet powerful concept: strain. In the macroscopic world, we experience strain as the deformation of an object under stress. Strain engineering involves deliberately introducing controlled amounts of strain into nanomaterials, typically by applying external forces. By carefully controlling the magnitude, direction, and type of strain applied, we can precisely tune the arrangement of atoms within a material. This atomic rearrangement disrupts the material's equilibrium state, altering its fundamental properties. To grasp the true power of strain engineering, it's crucial to understand how strain manifests itself at the atomic level. When we apply strain to a material, we are essentially altering the distances and angles between its constituent atoms. This increased resistance can manifest as a change in the material's electrical conductivity, making it more or less conductive depending on the type and degree of strain. Similarly, strain can also influence a material's optical properties by altering the way it interacts with light. The ability to manipulate a material's properties in this way opens up a world of possibilities for tailoring materials to specific needs. What makes strain engineering truly revolutionary is its ability to unlock hidden potential within materials, pushing them beyond their natural limits. Take graphene, for example. This one-atom-thick sheet of carbon atoms is already renowned for its exceptional strength and conductivity. However, by applying strategic strain, we can enhance these properties even further, creating graphene that is even stronger than diamond and more conductive than copper. Strain engineering allows us to transform materials that are already impressive in their own right into supermaterials with unprecedented capabilities. It also enables the creation of entirely new materials with exotic properties not found in nature. Imagine a material as thin as a single layer of atoms, yet stronger than steel. Strain, in its essence, is a force that induces deformation. Take, for instance, tensile strain. Applying this type of strain is akin to pulling on a microscopic rope, causing the atoms to move further apart. In fact, strain-engineered graphene can withstand forces far exceeding those that would shatter even the strongest steel. This ability to fine-tune both strength and flexibility opens up exciting possibilities for creating next-generation materials with exceptional mechanical properties. The flow of electricity, the lifeblood of our modern world, is governed by the movement of electrons within materials. Strain engineering, with its ability to manipulate atomic structure, provides an elegant way to choreograph this flow, transforming a material's electrical conductivity with remarkable precision. Applying strain can alter the spacing between copper atoms, creating a bumpy road for electrons, increasing resistance, and decreasing conductivity. Conversely, in certain semiconductors, strain can enhance conductivity by aligning atoms in a way that facilitates electron movement. By tailoring the electrical properties of materials at the nanoscale, strain engineering is paving the way for smaller, faster, and more energy-efficient electronic devices. The world around us is awash in a symphony of light, each color a unique wavelength interacting with the materials it encounters. Strain engineering adds another layer of artistry to this interaction, allowing us to manipulate a material's optical properties, its ability to absorb, emit, or reflect light with remarkable control. By altering the distances and angles between atoms, we can fine-tune a material's band gap, the energy required for electrons to jump between energy levels, which directly influences the wavelengths of light it absorbs or emits. This means we can essentially tune a material to glow a specific color by simply applying the right amount of strain. Strain engineering, therefore, is not just about manipulating light. It's about harnessing its energy with unprecedented efficiency. Heat, the transfer of thermal energy, is a constant presence in our world, and its management is crucial for a wide range of applications, from electronics to energy. Strain engineering, with its ability to manipulate atomic vibrations, offers an elegant way to choreograph the flow of heat at the nanoscale, controlling thermal conductivity with remarkable precision. For instance, applying strain to certain materials can disrupt the regular arrangement of atoms, creating obstacles that hinder the flow of heat. This reduction in thermal conductivity is particularly useful in thermoelectric devices, which convert heat energy into electrical energy and vice versa. From managing heat in nanoelectronics to developing more efficient energy conversion technologies, strain engineering is proving to be an invaluable tool for shaping the thermal landscape at the nanoscale. Imagine yourself as a sculptor, but instead of clay, you're molding materials at the atomic level. That's the essence of mechanical strain engineering. These robotic arms, equipped with nanoscale tips, can interact with individual nanostructures, applying controlled forces that stretch, squeeze, or bend them with remarkable accuracy. While effective, mechanical strain engineering often presents challenges in scalability. However, for research and development purposes, mechanical strain engineering remains an indispensable tool, allowing scientists to explore the fundamental relationship between strain and material properties. In the realm of strain engineering, the introduction of foreign elements into a material's pristine lattice might seem counterintuitive. Yet, this controlled contamination forms the basis of chemical strain engineering, a technique that leverages the subtle interactions between atoms to induce strain and alter material properties. By incorporating atoms or molecules of a different size or chemical nature into a host material, we can create localized strain fields that propagate through the material, altering its properties. One common method of chemical strain engineering is doping, where impurities are intentionally added to a material to modify its electrical properties. Chemical strain engineering, therefore, offers a versatile platform for tailoring material properties by carefully selecting the type and concentration of foreign elements introduced into the host lattice. Imagine trying to fit a square peg into a round hole. The mismatch in shape creates stress and strain as the peg forces its way in. This lattice mismatch, like the square peg in a round hole, creates strain in the growing material, forcing its atoms to conform to the underlying substrate structure. This uniform strain can have profound effects on the material's properties, altering its electronic band structure, optical properties, and even its magnetic behavior. Epitaxial strain engineering, therefore, offers a powerful tool for tailoring the properties of materials with atomic precision. Strain engineering is revolutionizing electronics, making devices faster, smaller, and more energy efficient. Imagine a smartphone that charges in minutes or a computer processor that operates at lightning speed without overheating. Strain engineering also boosts solar panel efficiency, converting sunlight into electricity more effectively. Transistors, the microscopic gatekeepers in electronics, benefit greatly from strained silicon. Strained silicon enhances electron mobility, leading to faster switching speeds and better performance. Strain engineering is also improving battery performance, increasing lithium storage for longer runtimes. Imagine electric cars traveling hundreds of miles on a single charge or smartphones lasting for days. Strain engineering is pivotal in developing next-generation solar cells, making solar energy more efficient and cost-effective. Imagine a world where bridges can monitor their own structural integrity, alerting engineers to potential problems before they become catastrophic. Or envision wearable health sensors so sensitive that they can detect subtle changes in our bodies, providing early warning signs of illness. This is the promise of strain-engineered sensors, leveraging the interplay between strain and electrical signals to detect physical phenomena with unprecedented sensitivity. At the heart of these sensors lies the piezoelectric effect, where materials generate voltage under mechanical stress. Strain engineering fine-tunes these effects, creating highly sensitive sensors for various applications. In structural health monitoring, strain sensors and infrastructure provide real-time data on stress and vibration. In healthcare, these sensors enable wearable devices to track vital signs and detect early signs of disease. Imagine a world bathed in brilliant, energy-efficient light, where information travels at the speed of light through optical fibers thinner than a human hair. Strain engineering is pivotal in advancing photonics, enabling faster, smaller, and more efficient optical devices. It helps confine light to small dimensions, crucial for compact devices. By manipulating the refractive index, we guide light along desired paths. This is key in creating photonic crystals that trap and guide light precisely. Strain engineering also fine-tunes quantum dots, enhancing light emitters for various applications. Imagine a world where computers solve problems in seconds that would take classical computers billions of years. Communication is perfectly secure thanks to quantum mechanics. This is the promise of quantum technologies. Strain engineering is a powerful tool for manipulating delicate quantum states. It fine-tunes energy levels to create stable qubits. In diamonds, strain creates NV centers, hosting electron spins as qubits. Strain engineering aids in developing secure quantum communication systems. Straining materials like lithium niobate helps generate entangled photons for scalable networks. Strain engineering manipulates matter at the atomic level, leading to potential quantum breakthroughs. As we stand at the cusp of a new technological era, strain engineering is poised to play an increasingly pivotal role, not as a standalone field, but as a unifying force, weaving together diverse disciplines like nanoelectronics, photonics, and biotechnology. Imagine a future where flexible electronic devices, seamlessly integrated into our clothing or even our bodies, can monitor our health, connect us to the internet, and even harvest energy from our movements. This vision of a hyper-connected, intelligent world hinges on the development of materials with unprecedented properties, and strain engineering is providing the tools to make it a reality. One exciting area of convergence is the integration of strain-engineered materials into nanoelectronic and photonic devices. Imagine a computer chip where electrons flow effortlessly through strained silicon channels, while photons, the particles of light, zip through adjacent optical waveguides, all precisely controlled by strain-engineered photonic crystals. Such hybrid devices could revolutionize computing, enabling faster processing speeds, lower power consumption, and entirely new functionalities. Beyond electronics, strain engineering is opening up exciting possibilities for integrating electronics with biological systems. Imagine flexible, biocompatible sensors that can be implanted into the body to monitor vital signs or deliver targeted drug therapies, all powered wirelessly by strain-engineered energy harvesters that convert the body's own movements into electricity. As the global demand for energy and resources continues to escalate, the need for sustainable technologies has never been more critical. Strain engineering enhances material properties and enables new functionalities, emerging as a key player in the quest for a greener future. Imagine buildings purifying air and generating solar energy, while vehicles run on efficient fuel cells powered by strain-engineered catalysts. Strain engineering enhances solar cells, making them more efficient at converting sunlight into electricity. It also plays a crucial role in developing next-generation batteries, essential for storing renewable energy and powering electric vehicles. Strain engineering enables highly sensitive sensors for monitoring pollution, contributing to a cleaner environment. The future of strain engineering is not one of isolated breakthroughs, but of synergistic advancements, fueled by collaboration across disciplines. Imagine materials scientists working hand-in-hand with electrical engineers, physicists, and biologists, each bringing their unique expertise to bear on complex challenges, pushing the boundaries of what's possible with strain-engineered materials. This interdisciplinary approach is essential for tackling the grand challenges facing humanity, from developing new energy solutions to combating climate change and advancing healthcare. The complexity of these challenges demands a united front, a convergence of minds and expertise from diverse fields. Imagine physicists using advanced modeling techniques to predict the behavior of strain-engineered materials at the atomic level, guiding materials scientists in the synthesis of new materials with tailored properties. Meanwhile, electrical engineers could be designing novel devices that leverage these materials, while biologists explore their potential for biomedical applications. This interconnected web of knowledge and expertise is where true innovation flourishes. It's about breaking down the silos that often separate scientific disciplines, fostering open communication, and embracing a spirit of collaboration where the collective knowledge of many minds can be harnessed to address the world's most pressing challenges. As we conclude our exploration of strain-engineered nanomaterials, the profound ability to manipulate matter at its most fundamental level, atom by atom, emerges. Stretching, compressing, or twisting atomic bonds unlocks hidden potential within materials, transforming diverse fields. Imagine flexible, self-healing electronics seamlessly integrated into our lives. Envision a world powered by efficient solar cells and batteries with abundant, sustainable energy. Picture medical devices diagnosing and treating diseases with precision. These glimpses into the future are shaped by strain engineering. As we push the boundaries of this technology, more groundbreaking applications will emerge. The journey ahead is filled with exciting possibilities, limited only by our imagination and willingness to explore. Strain engineering is a paradigm shift in material interaction, empowering us to design materials with tailored properties. In the hands of visionary scientists and engineers, strain engineering unlocks a future where materials are active contributors to a sustainable, connected, and healthier world.